and welcome to another WJEC A-Level Physics question. This is question 1 from June 2015's Unit 4 paper, and it's basically on kinetic theory, which is nowadays in Unit 3. So we're told that some oxygen gases are held in a sealed container, and we're asked to explain in clear steps using the kinetic theory and Newton's laws of motion how the oxygen exerts pressure on the walls of the container. So the first point we're going to have here is that the oxygen molecules collide with the walls of the container. Now in doing so, those oxygen molecules will change their momentum. They'll have some momentum initially in the positive direction before they hit the wall. Once they rebound, even if they're moving at the same speed, which would be a consequence of the fact that we assume that collisions are elastic, their momentum is different because their velocity is different. So let's summarize that and just simply say that, therefore, there's a change of momentum for the molecules. Now this is where we can get in Newton's second law, so I'm just going to call it N2 for Newton's second law. Newton's second law tells us that if there's a change of momentum, that the size of a resultant force is proportional to the rate of change of momentum. But this force is the force exerted on the molecules by the wall. So now we can use Newton's third law. So Newton's third law tells us then that the molecules exert an equal and opposite force on the walls. If the molecules are exerting a force on the walls, then the pressure exerted on the walls is going to be equal to the force divided by the area of the walls. So let's just say something like the total force of all the molecules divided by the area of the wall gives us the pressure. So the main points here are, first of all, that there's collisions between the oxygen molecules and the walls. The oxygen molecules' momentum changes, therefore the walls exert a force on them. Newton's third law tells us they exert a force on the walls, and the total force divided by the area gives us the pressure. Next, we're given one of the ideal gas equations, PV equals 1/3 Nmc squared bar. We've got to state the meanings of these terms, so be a little bit careful. Capital N is the total number of molecules. Little m is the mass of a molecule, one molecule. So don't say it's the mass of the molecules, because that almost implies you're talking about the total mass of all the molecules. So make it clear it's the mass of one molecule. C squared bar is the mean square speed of the molecules. And remember, that's found by adding together the squares of the speeds of the individual molecules and dividing by the total number of molecules. The question continues by giving us some information about the container. It's got a volume of 0.7 meters cubed. It holds oxygen gas at a pressure of 4 times 10 to the 5 pascals and a temperature 288 Kelvin. And we're told that the relative molecular mass of oxygen is 32. So next we've got to find the number of moles of oxygen gas in the container. So let's just use PV equals nRT. N is going to be PV over RT. Pressure 4 times 10 to the 5 times the volume of 0.7 over 8.31 times 288. If we put those numbers into the calculator, you get an answer that's very close to 117 moles, 116.99. Next, we need to find the Rms speed of the gas molecules. So here we can use P equals 1/3 rho c squared bar, or PV equals 1/3 nmc squared bar. They're both basically the same equation. First of all, we need to find the density. The density is the mass over the volume. The mass is 117 moles, and each mole has a mass of 32 grams. The volume is 0.7 meters cubed. So what do we get there? We get a density of 5.3 roughly kilograms per meter cubed. CRMS then will be the square root of 3p over rho. So square root of 3 times the pressure, 4 times 10 to the 5, over that density of 5.3. And that gives us 474 meters per second, which would be a sensible value. Finally, we're asked, in practice oxygen is not an ideal gas. Give one reason for this. Well, we could go for things like anything that goes against the kinetic theory assumptions. So for example, we could say that collisions with the moles of the container aren't elastic and so forth. Or we can go for the idea that oxygen doesn't obey Boyle's law at all temperatures. And that's what I'm going to go for this option here. All temperatures and pressures. Thank you very much for listening. Please remember to like and subscribe, and if you like, you can ask any questions below this video. Goodbye.